Today, I will introduce machine learning, but this is a very introductory presentation. So if you are a pro at machine learning and you've been using it for your PhD for years, you may be very bored today. But if you have no idea what machine learning really is, and you're curious to grasp the concept, and you're curious how you could get into it using Julia, this is really targeting you. So the current dominant paradigm of artificial intelligence is really to feed very large amount of data to algorithm. So it's really a data-driven approach, and it's all about learning. And learning for an algorithm really means strengthening some pathways. And today we will use the example of image recognition. So if you have an image which has a large number of pixels, if you had to program pixel by pixel what a picture could be, that would be really a daunting task. It's something that people have long thought that computers would never be able to do. But instead of explicitly programming what each pixel could be to represent certain objects, we feed a large amount of examples that are in the form of pairs of image and their associated label. For instance, an image of a cat and the label cat. And we feed all of this to a neural network, and the process of machine learning is what allows to develop the algorithm without being explicitly programmed. So to give a very broad definition of machine learning, it's computer programs or algorithms whose performance at a task, for instance, identifying objects in an image, improves with experience. And experience, really, that means data. And in the realm of machine learning, neural networks have really become huge. And there, the idea, the concept actually started in the 50s, and it's inspired by biological neurons. Biological neurons, they are a cell. It's electrically excitable, and you have some dendrites that collect some input. Then you have a body that processes the input, and then an axon transmits the output to another neuron. And artificial neurons are, of course, the way they function is very different, but the design is analogous. You have inputs that are weighted and summed, and this weighted sum is then passed through an activation function and gives an output. So the idea is similar. Now, if we look at a more realistic image, a drawing of a biological neuron, rather than the very simplistic schematic that we saw at first, we can see that the number of branching in a neuron is incredible. And these neurons then form in biological systems crazy neural networks. In black here, those are actually blood vessels. Those aren't the neurons. The neurons are in green, and you can see there's an extreme density of an incredible number of connections. And the human brain, for instance, are close to 100 billion neurons. So, of course, the level of complexity is not yet something that we can reproduce with artificial systems. But if we could scale up to that level of complexity, I mean, it's really hard to tell what those artificial systems would be able to. So how do those artificial neurons connect to each other to form a network, to form an artificial neural network? Instead of having the level of complexity that you have in biological systems, they are organized into layers. This is the simplest neural network possible. It is a single layer neural network. When we count layers in neural networks, we only count the number of hidden layers. So a neural network has first an input layer. In the case of an image, which is what we'll talk about today, those would be individual pixels, for instance. So you would have the size of the input layer would be the number of pixels you have. So it's a vector. Then in the simplest neural network possible, which is a single layer, you have only one hidden layer, and then you have the output layer. This one is also a feed-forward neural network in that the information moves from the input to the output. It doesn't create loops, it doesn't go backward, so that's also a very simple structure. And it is also fully connected or dense in that, as you can see, every single element, unit or node is connected to all of the other ones. So this input, for instance, connects to every single hidden node, and etc. But of course, you can scale up the complexity. This is still fully connected. It is still feed forward, but now we have two hidden layers. This is our input layer, hidden layer number 1, hidden layer number 2, and the output layer. So when we have a single layer, we call those shallow neural networks. And when we have multiple layers, so 2 and more, we call those deep neural networks. So a deep neural network is simply a neural network that has a depth, which is like the number of hidden layers of at least 2. Now, to go back last time to this analogy with the biological system, neurons, biological neurons, have a threshold potential. You have the dendrites that collect information from a number of neurons, and then you have an all or nothing response in the form of an electrochemical pulse. And so when the input reaches a certain threshold, you have a form of switch that's passed on. So you have either no response if you are below the threshold, or a full response if you are above the threshold. Greater stimuli don't produce stronger signals. What they do produce is an increase in the firing frequency. So this can be found in an analogous manner also in the artificial neuron, because so as I presented earlier, you have those weights and they're summed up. So this weighted sum is then passed to an activation function. And the activation function could be thought of a little bit as this threshold potential. And many activation functions have been tried. And the one people use depends on the problem at hand, also on the computing budget, because some are more demanding than others. And over time, new ones are being developed. One of the simplest one is the sigmoid curve. The Relu is one of the most popular. It's one that it's a maximum for positive values. So below 0, it's a flat line. Any negative value is transformed into a 0, and then positive values are linearly increasing. But like that's the mish and the swish and variations of the Relu, such as the leaky Relu. So depending on what you want, the sigmoid will, depending on whether you want a switch that will go between -1 and +1, or between 0 and 1, and depending on the behavior, you will choose one or another. But all these activation functions are kind of binary deciders. They're very much the equivalent of the on-off switch of our threshold potential. And later on, we will talk about another type of activation functions. So something else that gets added to the artificial neuron is what's called a bias. So in addition to these inputs and their weights, you have an additional bias which can also be weighted, and that allows to shift the output of the activation function to the right or to the left. This offset allows to reach values that you would never reach otherwise, because if you think of the sigmoid function, for instance, when you play with it, it will always go through 0, and maybe that's not what you want. So the bias allows to adjust this. But now, okay, that's a very broad, basic, theoretical description of what a neural network is, but how do they actually learn? What does it mean to learn? In fact, what they do in an iterative manner, which means over different repetitions, is that they adjust those weights and biases. And that's what creates the process that we call learning. So there are many types of learning now, but the only two I will mention briefly are supervised learning, in which you have a training set of examples. So you have pairs of inputs and outputs, and these pairs are used to find the relationship between input and outputs. So the classic examples that you've used many times without ever thinking of it as a form of machine learning is regression. A regression is a form of supervised learning in that you provide to your model some known pairs of or labeled inputs. So you have the input and its label, and from this you infer a relationship between input and output, and then you use this relationship to extrapolate to novel data to predict the outputs from novel input data. In the situation that we will look at today, when you want to recognize images, it's also a case of supervised learning, but it's a case of classification. So instead of having continuous outputs, as in the case of regression, you have discrete outputs. You have a number of boxes, for instance, cat and dog and something else. But then there is also unsupervised learning. In that case, you don't have labeled data. You don't have a set of X's with their Y's labels. You only have X's. And the goal here is to look for structure within the data. And examples you might have used without thinking of it as a form of machine learning either is PCA, or any form of clustering or network analysis, market segmentation. All these are unsupervised learning examples. One that is really, really fun, you should, if you haven't heard of it, you should really look into it because it's astonishing. A very simple algorithm allows to sort the cocktail party problem. If you have a big crowd of people, lots of noise, lots of conversation, and you have two different microphones that record the conversation, they will be, because there are different places in space, they will hear different inputs at different relative outputs, and that data is enough with a very simple algorithm to almost perfectly separate the signal so that you can extract one source of noise, like one speaker, out of the mess of the cocktail party noise. I find it mind-blowing. That's such a one-liner algorithm can do this so perfectly. So that would be a case of unsupervised learning, because it is the algorithm is finding some structure in the data without being given pairs of data. So now you have that data. How does machine learning work? Well, the cross-entropy loss function is the distance between the predicted distribution, so what the model predicts, and the real distribution. And the big objective of machine learning is minimizing it. Machine learning is about minimizing the loss function or the cost function. And a very classic approach is to use gradient descent. So over a number of repetitions, the weights and biases of the algorithms are being adjusted a little bit each time, and the length of the step depend on your algorithm. But eventually, the goal is to minimize your loss function. And gradient descent can be done in a number of ways. There is what is called batch gradient descent, in which you use all of your examples. So, for instance, all of your input-output pairs in each iteration. And if you have a huge data set, that's a very slow process, because your parameters will only be adjusted at the end of the iteration. So you'll have to go through a huge amount of data before any adjustment is being made. And also, if you have really a large amount of data, probably not all of it is all that useful. So another approach is stochastic gradient descent. In this case, you have only one example, so one input-output pair in each iteration. So it goes much faster, obviously, because after each example, the algorithm adjusts the parameters. On the other hand, it doesn't allow vectorization, because you pass elements one at a time. So a third and kind of intermediate approach that is very popular is called mini-batch size or mini-batch gradient descent. It allows to, it's much faster than the full batch because your mini batch, and you choose the size of your mini batch that you want, is only a subset of your full data set. But it allows parallelization, because within your mini batch, the examples can be processed in parallel. So it's kind of the intermediate approach that is the most common. And in 2014, a variation of it called ADAM, or the ADAM optimizer, was published. And it's a fairly popular optimizer, and we will be looking at it when we move on to Julia. So there are many, many challenges, obviously, and many complexities in developing those neural networks, but probably the most common problem that people can fall into is overfitting. So overfitting is when some noise of the data is being extracted as if it were meaningful. Well, in fact, it doesn't have any predictive power. Like here, for instance, if the goal is to separate the blue and the red dots, the green line is overfitted, because it's a perfect fit of our example data, but it's too good a fit, because it matches every single variation of the data. So what it represents is not really the meaningful generalizable structure of the data, but this very specific case. And you can imagine that a different data set wouldn't be separated very well by this green line, while the black line is a non-overfitted model. Like that's what you want to aim for. Underfitting, on the other hand, would be, for instance, to pass a straight line through this. If you don't have enough parameters, too many parameters, you're overfitting, but too few, you're underfitting, and the straight line here would also not have a huge predictive power. So how do you prevent overfitting? There are methods of regularization that allow this, for instance, by adding a penalty to the loss function. And I won't get into details there, but you can play with your loss function. There's also early stopping, of course. Also, so when I presented the structure of neural networks, there is the depth. Those are the number of hidden layers that you have. But there's also the breadth. And the breadth is the number of neurons that you have in each layer. So if you increase the depth and decrease the breadth, so if you have deeper neural networks, that reduces the number of parameters a lot. And that's a good way to prevent overfitting. But it creates its own issues, because too deep neural networks also create problems such as vanishing and exploding gradient problems. And I won't present them here, but basically it's hard to reach a minimum if in the case of deep neural networks. So another option to prevent overfitting is to look at the type of data that you have and to find a neural architecture that is adapted to your data. And that allows to have fewer parameters and also some shared parameters. And I will very briefly present two types of structured neural networks that are adapted to different types of data. They're convolutional neural network and recurrent neural network. So convolutional neural network, or CNN, is what is almost always used for image recognition. Its perfect application is when you have data that is spatially structured. In a fully connected layer, which is the kind of neural networks that the kind of layers that I presented earlier on, each neuron receives input from every element of the previous layer. Remember these early diagrams, you had connections between all the nodes. So if in an image, each pixel is an input, and it's even more than that. If you have a black and white image, you have indeed each pixel being one input. But if you have an RGB, like a color image, then you have 3 inputs per pixel, because you have the greens, the reds, and the blues. So for very large images with a lot of pixels, and if they are in color, very quickly you end up with insanely huge sizes for the input vector, and then you need a very large number of neurons, which gives you a crazy number of parameters, and that leads to overfitting potentially, and also it requires a huge computational power that's just not available. Convolutional layers, on the other hand, instead of having each neuron connected to all the neurons of the adjacent layers, neurons receive input from only a sub-area, which is called a local receptive field of the previous layer. So it reduces the number of parameters. And you can have a way to move this local receptive field across the image following a certain step that is called a stride. And so the size of the sub-area and the length of the stride are all components that you can play with. But from each time you have convolution, the number of the dimension of the data is going to be reduced. And optionally, in convolutional neural network, you can also do pooling, in which you combine the outputs of the neurons in a sub-area to reduce the dimension further. And so pooling could be average pooling, but often it is max pooling. And in that case, you take the maximum value of your sub-area, and then again, you have that stride that moves your sub-area across the image. So all this may seem a bit messy and confusing, but the main idea to keep from this is that convolutional neural networks are adapted to data that is spatially structured, such as images. The goal is to, instead of considering, in the case of an image, every single pixel independent of each other, as if they had absolutely zero spatial connection, it's a way to use the spatial structure of the image to reduce the number of parameters and make the computational demand a lot lower. And it's proved extremely successful. Another type of structured neural networks are recurrent neural networks, or RNN. And these ones are typically used for text or speech recognition. They're used when the data is structured again, but it's structured in the form of a chain. When you speak, words don't come out at random. And their meaning, depending on words that came before them and words that will come after them, varies. So, and it's a linear structure. This order matters a lot. And in recurrent neural network, instead of having this feed-forward structure where things only go forward, you have all sorts of looping going on. And in the example of long, short-term memory, you have a system of gates that add a level of information as to relation of elements compared to each other. And I won't get into this today, but just remember recurrent neural network. Recurrent, that's really what it means. Like there are recurring instances within the network in the form of loops, and they're used for mostly speech recognition. So all this was very theoretical. Now let's look a little bit into some very basic implementation. And how do we go about implementing all these ideas? There are many machine learning libraries. The most popular and the most used are PyTorch and TensorFlow, because they're developed by Facebook and Google. So those are really huge libraries, and they can be used through various interfaces, but their most common interface is Python, and Python is also an extremely popular language. So yeah, PyTorch and TensorFlow are very big out there. But Julia syntax is really well suited for the implementation of mathematical models. Julia is really a very, very mathematical language. So that's very attractive in the case of machine learning. GPU kernels can also be written directly in Julia. So that's pretty cool, because as you can imagine, machine learning is very computationally intensive. And it's also, because there's a lot of vectorized calculations going on, it's also particularly well suited for being run on GPUs. So to be able to write directly to the GPU in Julia, that's quite cool. Another thing is that Julia's speed, thanks to just-in-time and other particularity of Julia, make it quite nice for a field that is very computationally hungry. But there are other things that I didn't mention here, and that are interesting in research. Maybe not to scale up to industry at this point, but if you're interested in some form of modeling or differential equations, or there are a lot of packages that are in Julia that are very interesting for a lot of or Bayesian modeling. You can combine all of that with, for instance, Flux. So being able to combine a lot of really cool Julia tools with a package for machine learning, that's pretty appealing. And so Julia has seen a pretty large development of machine learning packages. If you look for tags, machine learning packages that are tagged, if you look for packages in Julia that are tagged for machine learning, you might be surprised by the number of returns you will get. This is only a subset, but Flux is probably the most popular, and it's a machine learning stack. But you have also KNet, which is another deep learning framework. There is a wrapper for TensorFlow. Turing is for probabilistic machine learning. MLJ is another framework to compose machine learning models. Scikit-learn allows to implement the scikit-learn API. But there are others. So really, it's been pretty huge in Julia, and it really isn't surprising considering how suited Julia is for calculus and mathematical models. So today we'll have a quick little glance at Flux, which is really one of the most popular machine learning package in Julia. And we will look at the most classic example of a neural network. It's the classification of the MNIST dataset. So this dataset are pairs of images of handwritten digits and their labels. And they've been used, and they're still used often to compare different approaches, to benchmark things, or also to introduce the whole concept of image recognition. Because you have those handwritten digits that have been transformed into images, and they're each made of an image of 28 by 28 pixels along a grayscale. So you don't have 3 RGB layers. You only have one layer. So each image is going to be 28 times 28 times 1 unit, because you have 28 pixel square, but only one color channel. And the labels are the actual digits that those images represent. So you have 10 labels, 0 to 9. And so you have those pairs, and the goal is to have the machine identify the handwritten digit. For instance, say that, okay, this is a 0, this is a 1, etc. So basically, it's a classification problem. The machine has to classify each image into 10 different categories, and they're discrete categories. The dataset has 60,000 images to train, and then 10,000 images to test. And it's an open source dataset. You can download it directly, but it's also commonly available in PyTorch, TensorFlow, Flux, etc. So how to get started if you want to get into machine learning with Julia? There is one package. It's called well, it's not actually a package, but it's one project in Julia. It's on GitHub, and it's called the Model Zoo. And it provides many examples of approaches in various domains. And for instance, there is the domain of vision, and the MNIST is being used by a number of different models. And those are great starting points. And what is really interesting is that it's under extremely heavy development. When I looked at some of the Model Zoo as I was preparing for this webinar, I played with them, I ran them, I looked at them, and then a few days later, I would pull from the GitHub repo, and there were lots of fixes. Some bugs were removed, things were written in a nicer way, it was expanded. So things that just weren't working still a week ago, now they're fixed. And I still find some things that are behaving a bit weirdly, but again, like it keeps being improved. And I think that's actually really cool because first, machine learning is itself a field of very active development. So having a very active team is necessary when the field is changing so fast. But it's also really cool because as I look at the models and how they evolve over time, I can see different approaches. I can see how things can be written in different ways, and I find it very pedagogical. So this, I think, is really the best starting point with Flux, particularly since, unlike PyTorch and TensorFlow and those bigger things, it doesn't have at this point a lot of documentation or tutorial. There is documentation out there, but it's a bit hard to follow, and it's very succinct. So the examples are, I think, the best place to go about it. So let's have a look at a few of the functions in those examples before we look at the actual examples. For those who aren't familiar with Julia, so first you have to install packages. But once the packages are installed, to load a package, the function is using. So using Flux allows me to make the package Flux available. And then you can run things like using Flux, and a number of functions. This isn't necessary, but what it does is that for the rest of the session, instead of having to write Flux dot one hot batch, you can just write one hot batch. So it makes these function names available in the current namespace. So it's just a little convenience trick. Then the training data is under the Flux package, under data, it's the MNIST. The images, that's the images function. The labels, that's the labels function. We can create arrays with that data that we can call, for instance, IMG for the images and lab for the labels. So what does the image data look like? We have an array of images and one of labels. Let's first look at the images. Typeof is the Julia function that allows you to see the type of an object. And because Julia is a very heavily typed language, that's something that's always very important. So images, it's a one-dimensional array of arrays, and those arrays are two-dimensional of a type that's called color types gray, which is some kind of thing of integers, some kind of fancy thing. Well, okay. What is the length of image? Well, it's 60,000. And we knew that. I mean, that makes sense because the training set is 60,000. So it's a one-dimensional array of 60,000 two-dimensional arrays, basically. if we look at the first element, so this is the way to index the first element of image, and unlike Python and many other languages, but like R, Julia starts indexing at 1, not 0. So this is the first element of the array. I can see that it's a two-dimensional array of the dimensions 28 by 28. So the first element of my big image array is one individual picture, and this picture is made of a two-dimensional array of 28 by 28. So each element of that array represents a pixel. And those pixels are grayscales in this format, and this format comes from a package in Julia that deals with images. So if we want to look at one individual pixel, now from our first image that we have indexed here, now we index the first element. So because our first array was a one-dimensional array, it was just 60 different images, so it was a vector, if you want. I only needed one index here. But now that element is a two-dimensional array because it's an image, so it has two dimensions. So to index it, I need two elements. And because I want the first pixel, it's 1, 1. So that gives me this weird value that represents the grayscale of that pixel. So this value is the top left pixel of the very first image of the training set. A way to transform this weird value that's not exactly easy to play with into something much more familiar is just to run it through float. Float is the Julia function that allows you to transform a value into a float. So we get a float, which is a lot nicer. Now, another Julia package that's very popular is called plots, and it's one of the common packages to plot things. If I plot the fifth element of my training image dataset, and the 8th one, and the 87th one, and the 2003rd one, and of course I chose those values totally arbitrarily, I get a plot, a visual of what they look like. The reason I have two plots here is because the internal plots, like plot image 5, that plots this. That allows me to plot the fifth element of the array, so the fifth image. And I do this 4 times because I have those 4 images. The outmost plot allows to combine them in a single plot, so that instead of having individual plots, it's a plot of plots. Okay, so we can see that the 5th image is a 9, the 8th one is a 3, etc. Now, let's look at the label data. So remember, we had image that was our training images, and we created the array lab, which are our training labels. So the type of lab is an integer. It's a one-dimensional array of integers, and its length is 60,000. So that also makes sense that we have 60,000. So one-dimensional array of 60,000 integers. And that makes sense because those are simply the labels. The labels are the actual digits that the images represent. And if I look at the very first element of this one-dimensional array, it's 5. Okay. So remember that the 5th, 8th, 87th, and 203rd images of our image object looked like this. Now, if I take the 5th, 8th, 87th, and 203rd element of the lab array, I get 9, 3, 3, and 8. 9, 3, 3, and 8. Okay, so yeah, that's what the training data looks like. It's 60,000 pairs of images of those handwritten digits and the corresponding labels. Now, a few functions that you will see in those model zoos that you may be a bit confused about. One hot batch. So one hot batch turns a batch of labels into a binary matrix. And one called performs the reverse operation. So what does that mean? If we take a very, very small subset of lab, so if we take the first 3 elements, we index the first 3 elements of our 60,000 long array. Now we have a one-dimensional array of 3 elements. Those are the first 3 labels, 5, 0, and 4. If I run one hot batch, if I run this into through the function one hot batch, what I get is what's called a one hot matrix. I have a binary matrix of zeros and ones, and so the values were 5, 0, and 4. Now, if you look at our binary matrix, 5, 0, and 4, yes. So this is the first element, second, third. Sorry, how does it work? 5. Yeah. So this would be the 0 in our labels. This is 1. This is 2, 3, 4, 5, 6, 7, 8, and 9, because we have 10 different categories from 0 to 9. So the first element is 0, 1, 2, 3, 4, 5. 5, that's what we had indeed as the first element of lab. The second element of lab was a 0, and indeed that's what we have here. It's a 0. And the third element was a 4, and indeed that's what we have here, 0, 1, 2, 3, 4. So basically, one hot batch allows to transform those values, 5, 0, and 4, into a binary matrix representing those values. And one called, as I said, is the reverse operation. So if now I pass our one hot batch into one called, I get back to the initial 3 elements, 5, 0, 4. Another thing that you will encounter in the model zoo, and it actually, this is not a Flux thing, this is a Julia thing, but you'll see it a lot, it's called splatting. So let's look at a very basic example of splatting. If you run this is the equivalent of writing 2 plus 3. You can write 2 plus 3 or plus as a function of, and then pass as argument of this function plus 2 and 3, you get 5. Okay. Now, if you assign these if you assign it to the object A, and you pass A as an argument of the function plus, you get an error, because the function plus requires a tuple. It requires a tuple is list is not the proper word. I'm not a computer scientist, so I'm not sure what the exact definition of a tuple is, but it requires a set of elements. Not a single element doesn't work in this case. But if instead of passing A to the function plus, if you pass A ... which is called splatting, then you get the proper output. So what splatting does basically is it allows to, it kind of fills in for missing elements. And when you work with vectorized, in a vectorized fashion, which you very often do in machine learning, splatting is extremely convenient. It saves a lot of typing. It's a great little convenience function, and you will encounter it a lot. Now, at the very beginning, sorry, when I talked about activation functions, when I made an analogy between a biological neuron and an artificial neuron, I presented a number of activation functions, and I mentioned that Relu, which is called the rectifier, was a popular one. This is what it looks like. It takes, for negative values, it takes zeros, but for positive values, it increases in a linear fashion. And it's an activation function that is popular because it's very simple to compute, as you can see, because it's not linear, but a big chunk of it is linear. The computations are very easy, so it doesn't require a lot of resource. And it works well in a number of cases. And in Flux, to implement Relu, you have the function Relu, which is very, very, very simple. As a side little note, in some cases, having zeros for negative values is a problem. So you have variations of Relus, like the leaky Relu that gently inclines downward, and other variations that allow to modify this which is useful in some situations. But the models used for the MNIST only use the Relu. Now, the sigmoid and the Relu and all these activation functions, they're great if you have a binary decision to make. So they're very useful within or in between your hidden layers. But at the very end of your neural networks, ultimately what you want to do is to decide between 10 different categories, 0 all the way to 9. So having a binary output wouldn't work. We need to be able to categorize between more than 2 boxes. And the softmax activation function is a big classic to that. And what it does is that it normalizes a vector of real numbers. So that means that the output of a softmax function all fall between 0 and 1, and they add to 1. So it changes it into a probability distribution, if you want. And that's great because it will give a very high weight to the most likely category, and then very small weights for the remaining categories. But because it changes things in a probability distribution type output, it's nicer than having just 1 and a bunch of zeros. So it's a very useful and very popular activation function at the very end of your neural networks whenever you have classification problems, which is very often the case in image recognition. And the softmax function in Flux is, again, very easily written as just softmax. And here is an example of softmax. Now, this is one shape that softmax can take. But while the Relu will always have the same overall shape, that's not true of the softmax function. In order to really see what the softmax function looks like, you would need a multi-dimensional space because because instead of outputting a vector, it outputs a tensor, and a tensor is a multi-dimensional array. But we're almost out of time, so let's have a quick look at two of those model zoos to work with the MNIST dataset. And you can find them online, and you should run them, and you should look at them, and hopefully those little bits and pieces and functions I've covered will help you. But this first example is a multi-layer perceptron. A perceptron is pretty much your basic unit, your basic neuron. It's the very first neuron that was created. So a multi-layer perceptron is a simple feed-forward arrangement of perceptrons. And it's not the best way to go about it for images. As I mentioned earlier, convolutional neural networks are a lot more efficient. But you can have an example of multi-layer perceptron. So here we're loading the packages and making some names available. We're also making some macros available. Macros are some meta programming abilities that Julia has and which are extremely handy. We're using the machine learning datasets, which is a package that has a lot of datasets, and then defining a number of arguments, creating some functions, etc., etc. Creating some functions to get the accuracy, then creating a training function, etc., etc. And at the end, we run our training function. So if you run this, you will get, first it takes a while to run. This basic example uses 10 epochs. So an epoch in machine learning is the use of all of our, the passage forward and back of all of the examples. So they are, so all the examples are being used 10 times in this example. And the results that you get, the accuracy that you get, both for the training data and for the test data, like those 10,000 test sets, is around, I just ran it this morning, 97% or something like that. So it's great. It's really great. But if you use a convolutional neural network, you get much, much better results. And it's also faster to run. So here you can have an example of a CNN. So, and then there are countless other examples. So obviously in 1 hour, there is no time to go over all of that. And I just wanted to kind of guide you towards being able to look at those examples by yourself. But a few last things that I would like to add is that the BSON package allows to save models in a binary JSON format. So that's a great way to save your models. And in machine learning, there is something called transfer learning, and it's very, very often used. Instead of starting with random values for your weights and biases, which would require models to run for a very long time and require huge data sizes, people often actually download some pre-trained models, and they benefit from the pre-acquired learning of these models, so that instead of random initialization, the weights have already come from another model. Of course, the models have to be related. They have to be on something similar, but it's a way to get very good results much faster and mostly using very small data sets. And the ONNX is a standard format for models, and there is an ONNX package that allows to read pre-trained models directly into Flux. So you can find pre-trained models for image recognition or whatever and directly bring them into Flux so that you can cut a huge amount of computing time by using better starting values than those random weights and biases. And finally, I mentioned earlier that Julia has a great GPU support. The QRA package can provide very, very easily functionality into Flux. So if you load this package, then the function GPU converts all the parameters that are within your models and moves everything to the GPU. And Flux itself, the model architecture, is kernel agnostic. It works both on CPU and GPU. So the only thing that needs to be converted are the actual parameters, and GPU takes care of that. So you can pass your model to the GPU function, and boom, you can use the GPU. And you can even, this is the pipe in Julia. So you have some code, you have your model or whatever, you can just put a pipe and poof, throw it into GPU, and that's that. It's as simple as that. And the function CPU converts things back and moves them back to the CPU. And if you look at the two models, things that I commented here are using CUDA API. This is a package that allows to test whether or not you have a CUDA GPU on your system. So if you run this, you will get a yes or no answer. And then if you uncomment this, the result of CUDA API is going to be passed into this conditional function. And if has CUDA, then CUDA arrays is loaded, and etc. And if not, nothing happens. So if you uncomment these lines, and if you add some pipes to the GPU function to all your models, you have a code that runs equally well on a system that doesn't have a GPU and a system that has a GPU. So for instance, if you work locally on a laptop and you don't have a GPU, you can run the script without any problem and tweak it and play with it. And one of the beauties of Julia is that it is very efficient, yet it feels like an interpreted language because you have an interactive shell and you communicate with it, unlike in a in a compiled language. And afterwards, that same code that was running on your laptop without a GPU, you can, once you have a script you're satisfied with, you can run it on the cluster, on Cedar, for instance, making use of the GPUs. So that's very convenient. So we're out of time, and maybe things were a little rushed at the end. I was hoping to look at those two models a little bit more, but my main goal was to really try to explain the very broad concepts of neural networks and to introduce you to Flux and to some of the very common functions that you will see in the model zoo, and then to encourage you to go have a look at the model zoo, run those models, poke at them, and hopefully tweak them in ways that work for your own explorations of machine learning. So if you have any questions, I would love to try to answer them.
Thank you, Marie. There were no questions in the chat so far.
Okay.
Please feel free to unmute yourself and ask a question via audio or type a question into the chat.
Oh, not also actually that. Sorry. Alex will post a link to the slides, but also so part of the WestGrid training material has a section on Julia and another section on machine learning. And because this is about machine learning and about Julia, the same presentation is in both sub-sites. In the webinar section, there is machine learning in Julia with Flux, and maybe, Alex, you could post a link to that page as well. This page has a comments and questions section at the end, and anybody with a GitHub account can post in it. So if you have questions at any point later on when you look at the model zoo and you play with things, feel very free to start a chat here, and others and myself will try to answer and discuss. So that's if you don't have questions yet, that's another option.